Now our speaker tonight is Dr. Bob Abel. He's a professor emeritus at Olympic College and a member of the DiRAC Institute in the Department of Astronomy at the University of Washington. He will talk tonight about the Vera Rubin Observatory and what this instrument will teach us. I know that you probably know this, it's in the Andes Mountains. And what I think is one of the fascinating things, it's got the largest digital camera ever built. I want you to.
That was going to be my surprise.
I thought it might be, sorry, whatever. And so then, so give a especially loud clapping for him because he's sort of disappointed. So I give you Bob Abel. Thank you very much.
Hey, everybody, let me start off with something very sciencey. So I just wanted to give, before I talk about the telescope, I just wanted to give just a little common background about some things we know about the universe. We think that about 13.8 billion years ago, the universe was a small ball of incredibly small, incredibly dense, incredibly hot, pure energy. As it expanded and cooled, a lot of particles precipitated out, the components of atoms, protons and neutrons and electrons. It was almost 400,000 years before the universe had expanded enough and cooled enough to where these particles were moving slow enough to where electrons could be captured by the protons and become neutral atoms. At that time, that's the first time light could actually escape into the universe. At that time, it was about most of them were just hydrogen atoms, and that's the very top row here. There's hydrogen, one proton and one electron. And maybe 1 out of 10 cases, 2 protons had fused together, which takes a lot of energy to do. And that's helium. They had 2 electrons. That was all there was. There was a little bit of lithium with 3 protons just for sanity, but mostly it was just hydrogen and a little bit of helium. That was it. I mean, you can see how big this chart is. These are all the elements you find in the solar system. They hadn't been created yet. As the universe expanded more and more, it wasn't completely uniform. And some of the clumpier areas collapsed gravitationally. And as they collapsed, they got harder and harder. And at some point, in some areas, they got so hot and so condensed that they started the fusion process. It takes billions of atmospheres of pressure and millions of degrees of temperature to shove protons together to make these heavier elements. And the first stars were able to, well, our star, it's taking hydrogen and fusing it together to make helium. Bigger stars can fuse bigger and bigger. At the end of its life, our star will have made carbon and oxygen mostly. It'll have covered perhaps the second row of the periodic table. And larger stars can get all the way up to middle way through the 4th table, shoving protons together to make bigger elements. When these big stars die, the bigger stars die, they run out of fuel and they collapse and they expand out rapidly, creating a shock wave. And that shock wave converts energy into more matter. It makes all the elements heavier than nickel and iron. So if you're wearing any piece of gold, that had to happen in something like a supernova detonation. So we're recycled stardust. 100 years ago, we didn't know any of this. We now know that stars come into groups that we call galaxies, and we know now that almost every star has planets orbiting it. We just didn't know this 100 years ago. Right now, we're learning about the universe faster than ever before, and I think in the next 15 years, the greatest leaps of knowledge will come from the Vera C. Rubin Observatory, which is what I'm going to talk about now. There's a picture of it. Okay. You notice it looks different. And you look down here, these naked people here, you can get some idea of how big the telescope is. All right. It's scheduled to begin operations next year on a mountaintop in Chile, up from La Serena. Is that okay? Okay. I'm going to talk about what it'll do and how it'll do it. So you know how almost all telescopes, they're great at looking further out, but what you lose is you lose peripheral vision, right? I mean, mostly on a major telescope, it's got a big dish to catch a lot of light, and it comes down to a small point, and you're looking at a certain star or groups of stars or a certain galaxy, small point of view so you can actually see things and just observe one item. Typically, an astronomer will get granted time on a telescope, and she'll get her hours in on the telescope, and that'll be her data. She'll process it and publish some papers and eventually release it to the public, you hope. And usually that's what happens. But it's designed to look at certain things. The Vera C. Rubin Observatory's telescope is designed to look at everything. All right. Its motto, which I didn't come up with, is wider, faster, deeper. The wider part is each image. Each image is 7 full moons wide. Okay. It has 7,500 times the viewing. It has 7,500 times the viewing area of the James Webb telescope, and the mirror is only slightly bigger. So it's designed to look wide. Faster. The faster part is it takes 30-second exposures, right? And what it does is it takes a large image for 30 seconds, gets the exposure, goes to another one, goes to another one, goes to another one. Every 3 nights, it covers the entire night sky. And it does that for 10 years. So you get a lot of repeat performances. The deeper part is its imaging ability. It can see objects that are at least 3,000 times further away than what I can see, even with my glasses on. So it's now, how does it do that? Let me describe that. So I'm going to get into the engineering a little bit. Doing okay so far? Okay, just give me a thumbs up there. You notice it's very squat, all right? Because it's got to move fast. It's got to take a 30-second image, and it's got to move, and you can see how big it is, and it's massive, all right? So here's how this is a unique mirror array. It's got 3 mirrors and 3 lenses. The first and third mirrors are made out of the same piece of glass, all right? This is a 27.5-foot diameter piece of glass, this primary mirror. But the primary mirror is this ring that you can see right here. And so light comes down, it comes down and hits that ring on the primary mirror. It reflects back up to the top with this secondary mirror, which has got a big hole in it for the camera. Comes down to the tertiary, or the third mirror, and then back through what is currently the largest optical lens in the world, through 2 more lenses and into the camera, which now you know is the largest digital camera in the world. Thanks, Barbara. This surface, I should mention, I'm kind of snide. This surface is so smooth. The smoothness is within 1/10 of a millionth of an inch. All right, it's a beautiful mirror, modern technology. This is the camera, the largest digital camera ever built. Fits into the second mirror, the secondary mirror. Its sensing service consists of pixels, and the pixels, when a photon hits one of those pixels, it registers an electron, and so you measure an electron for every pixel. It's very accurate. This surface has 3.2 billion pixels. Okay, if you have an iPhone 15, that's more pixels than 1,000 iPhone 15s. Here's a mock-up of that facility. Sit anywhere, Tom. You're welcome. And you can see just in this mock-up how big the full moon is compared to one picture. So you get some idea of how large the picture is. When you combine the number of pixels that are measuring each photon and the size of the lens, you get incredible resolution. With this telescope, you can look at 2 objects that are 3/10,000ths of a degree apart, and you can register them as 2 objects. So it's incredible resolution. It would take, to properly display one 30-second image, and it's taking 30-second images every night for 10 years. Just to display one of those would take 1,500 high-definition screens. As another example, I hope you can make this out. This is the Sphere in Las Vegas, if you're familiar with it. It's the largest indoor digital screen in the world. Here's the audience, and down here's you too. There's the edge right there. If I was to try to put one 30-second exposure up on that screen, the screen could only handle a little less than 1/12 of one image, one 30-second image. So you get some idea of what's going on. It's got incredible resolution. It sees deep. It takes images after image after image, and it repeats it for 10 years. All right. But it's got one more thing going for it. Color. You and I have you and I can see, we have cones that differentiate color, and they work, and there's some that work in the red and the green and the blue. And the colors we see depend on the fraction of each of those that comes in. It's a little more red, it's going to look redder, but we differentiate. That's where all our color comes from. The same thing happens with your phones, red, green, and blue. This telescope can use 6 different filters that cover the shortest wavelengths, actually shorter wavelengths than we can see even into the ultraviolet, to the longer wavelengths over on the right, and a little bit longer into the infrared that we can't see. And it's got 6 different color measurements, and it's measuring every photon. It is one of the best color discriminators in the world. And that's very useful for identifying all kinds of objects in the solar system, the universe, and beyond. Well, maybe there is a beyond. Here's the facility. It's on Cerro Pachón in Chile, coming online next year. This is from 2 months ago. If you see down here, the truck is carrying this hexagonal object. That's the primary mirror that was delivered either in April or May. Up here, and by the way, just this month, the camera made it down there. So things are looking up, literally. Here's where the telescope sits, right up in the top. The mirror is going to go into this facility down below first. Whoops. Is going to go into this facility down below first for to put this. It's actually already been done, to put the silvering on the mirror to turn it from a piece of glass into a real mirror. All right, and that has to be done regularly, a couple of times a year. And so that facility is built for that, but it's also got a whole bunch of servers, because think about what we're downloading every night. The download rate for all those images every night, and these get downloaded to the servers. They get sent to facilities in the United States, Chile, and France. Okay, 20 terabytes a night. That's if you've got an iPhone 15, it's hard to fill up, right? Well, one day would fill up over 160 iPhone 15s, and it's operating for 10 years. So much data that it's a 10-year mission, but in the first 2 months of operation, this telescope will acquire more data than all the telescopes in history combined, just in the first 2 months, and it's a 10-year operation. Okay. So during that time, you'll have about 800 images in the 6 different colors of each of tens of billions of galaxies. I'm not exaggerating. Billions and billions of stars in our galaxy and millions of solar system objects. So I'm going to talk a little about what it'll do, and I'm just going to start in our solar system and move out. Oh, there's our solar system. There's the Sun, Mercury, Venus, Earth, Mars, an asteroid belt, Jupiter, Saturn, Uranus, Neptune, Pluto, and the Kuiper belt. This telescope can't look at the Sun. Can't look at the moon. Can't look at any of the planets or their moons. They're too bright for this telescope. But it can look at asteroids. And asteroids can tell us a lot about the history of the solar system. The current models suggest that the outer planets, Jupiter and Saturn, Uranus and Neptune, were much further in during formation. And they migrated outward later. And as they did that, they disrupted a lot of the smaller bodies gravitationally moving around. At the time, there appear to have been many more planetoids, which would be objects that were big enough to where gravity they'd be heated up from collisions. Everything formed from collisions. They get big enough to where they heat up, and the denser materials would sink to the middle, to the center, just like happens in the planets, right? We've got a solid iron nickel core, okay? And so you'd have differentiation of materials. The metals would sink towards the center, the denser materials to the lowest part, and then you'd have stony materials and crust and carbonaceous material and ice. And so you had it all differentiated. When these planets moved out, we think that's what happened. These planetoids got hit, and they had all kinds of collisions. They ran into each other, and they broke apart. But now you've got chunks of core and chunks of stone. You've got different kinds of meteors, and they have colors. And I don't know if I mentioned this, but we're really good at measuring colors. So what we want to do is we want to classify these asteroids. We now know of thousands of asteroids. This will discover millions, like I said. First off, we can classify them by their orbits. If they're traveling in similar orbits, they probably belong to the same group. It's more than likely. but also from their color, we can tell what they're made of. And so we can take these broken pits and put them back together and figure out what they used to be, right? There are two main belts of asteroids. There's the cleverly named main asteroid belt between Mars and Jupiter, and the Kuiper belt, of which Pluto's a member, out further out. I should mention, Pluto, the Kuiper belt is about as far out as we know, and it's about 50 to 100 times further out from the sun than we are. But the stars are so far apart that stable orbits around the sun can exist for over 100,000 times further out from the sun than we are. That's like 1,000 trillion times more volume than we can see. So there's a lot going on out there. And we know there's stuff out there because long-term comets come in from there and go out, and their orbits are very big. So we can use the color and the resolution and the fact that we're constantly taking images so that we can see how they're moving and get their orbits. We can use that to figure more out about the history of the asteroids and the history of the solar system. But perhaps we're more interested in the future. This is the moon. 100 years ago, it was thought that the craters on the moon were all due to volcanoes, because that's the only way we knew how to make craters. Now we know it's due to impacts. And every planet and every moon around this in the solar system has been hit repeatedly by asteroid impacts. It doesn't show up as much on the Earth. First, we've got an atmosphere, and a lot of stuff burns up before it gets to the ground. Secondly, we have erosion, plate tectonics, and so a lot of that stuff disappears after a while. So it's understandable that it wasn't understood where these things came from. This is Meteor Crater in Arizona. Many of you have been there. I want it, but I haven't yet. It's about 50,000 years old. 50,000 years ago, an object about 50 yards in diameter, like that. Okay, just to give you an idea. Crashed in. It was about 300,000 tons, moving at 27,000 miles an hour. When it hit, it released the energy of, It released the energy of about 150 World War II atomic bombs due to that impact. Before it hit, it produced a shock wave. At the time, there were forests in this area. It produced a shock wave that would have leveled the forest for miles around. Okay, if this happened today, that would be, it would be catastrophic, right? 66 million years ago, the reign of the dinosaurs ended with the arrival of a 6 to 9 mile wide asteroid, which landed in the Yucatan Peninsula. This would have the energy of about 1 billion World War II atomic bombs. It would have produced tsunamis that were about a mile high, moving at supersonic speeds. It would have flash burned the entire surface of the Earth. It would have raised up so much dust that photosynthesis would have stopped for on the order of a year. All right, we don't want that to happen. So that's why we're paying attention. There are asteroids everywhere, and we are trying to locate and perfect and really nail down the orbits of anything in the near Earth and figure out migration habits of asteroids. We want to find just about every asteroid bigger than 140 yards and nail its course down and find out what its trajectory is. It's part of a congressional mandate, but also it's like a really good idea, right? So it's not a matter of if we're going to get a meteor strike, it's just a matter of when. And if we can spot these early enough, we can do something to move these asteroids out of the way. Because if we know their trajectories, we can figure things out, up to like 100 or 200 years in advance. And so we have time to do something about it. That's the main thrust of our solar system work. It's a good idea. On a lighter note, commercial applications are available. Did I mention we're really good at measuring color? So we can figure out what asteroids are made of, and companies can go out and mine them. And it sounds like future work, but I easily found three companies that's their sole purpose: Astroforge, Carmen Plus, and Transastra. Carmen Plus is currently scheduled to launch a mining mission in 2026. Yeah, so the future could be coming up. Oh, it's really expensive to launch stuff from Earth, and if you can mine things out in space, they move it into a lunar orbit and work it from there, you can save a lot of money. You can make a lot of money. Lastly, in the solar system, I love this part. In the last couple of years, we found 2 objects whose trajectories indicate that they came from outside the solar system. They didn't start off with our star, okay? So the Rubin Observatory, by looking every night all the time, is going to find more of these. And how cool is it to find out about other stars by having them send stuff to us? So I'm looking forward to that. Now, beyond the stars, or beyond the solar system, we have to figure out how far things are away. And we do that with a series of distance candles that have already been created. And the Rubin Observatory will help us in all these phases. The first one is, the first distance candle is parallax. We have 2 eyes so that when we look with one eye, we see the background. I'm looking at you, Sue, and I see the background at one angle, and now I look at the other eye and I see the background with another angle, and my eyes can solve that geometry problem and figure out about how far away it is. Right now, let's say, here's the sun, and there's the Earth, and the Earth has got a telescope on it, and it takes an image. 6 months later, here's the sun, and here's the Earth. And now I take another image, and I've got a baseline of 186 million miles. I can get parallaxes out to 200 to 300 light years with that. And within that volume, I can start nailing down what the stars are like. So there are certain stars that breathe. They oscillate, okay, on the order of a fraction of a day to 100 days. RR Lyra and Cepheid variables, different kinds of stars. And it's related to how bright they are. So if we know how far away it is and how bright it is, we can figure out how bright it actually is, how bright we're seeing it. So if we know how far it is, we know how bright it actually is. And now we can categorize these. And so now these fluctuating stars, we can go out further than parallax will take us. And we can say, well, it's fluctuating at this rate. It must be this bright. Okay, so I know how bright I'm receiving it. I know how bright it should be. So now I know the distance. We can find these in other galaxies. And then we start looking at other things like supernova detonations in galaxies where we know how far apart they are. And we can classify the supernova detonations so we know how big it was and how big it should be. And then we can go further back and further back. And there's a series of ladders we use to figure out where everything is in the universe. And this will help us in all phases. Stars. Okay, did you notice they're really colorful? I think I might have mentioned that we're really good at measuring color. And we can classify things better than any telescope ever could. And that's some of the work I'm doing. Using machine learning technology to categorize things according to color. These are the seeds of the universe. They produce the elements that we use. And when they die, they produce. They do the first half of the periodic table while they're alive, and then they spew out the rest. The shock waves make the rest of them after they die. That'll get you about the first half when they're living. That'll get you about down to here, middle way through the table, and then the detonations of the big stars will get you all the way through the rest. So we have all these stars. More stars, billions and billions of stars. And what do you do with that? You can't look at very many individual stars. You can't study them by doing that, but you can do it with statistics. If an alien came down, for example, and was looking at this group, and I had an hour and I had all kinds of instrumentation, and I looked at this group, I could figure out a lot about human beings, right? I'd get a lot of information. But what if instead this alien came down and spend an hour looking at 4 billion human beings? In an hour, you could figure out our entire life cycle. You could figure out our wants, our desires. You'd have all these images and you'd store them and you'd be able to look at them. All right, that's what we can do with these stars. We'll be able to categorize them and follow processes better than ever before. We've already started working on this with other surveys where we can actually see dwarf galaxies that have been captured by the Milky Way, by our galaxy. And we see streams of stars moving in one direction. So we're starting to get an idea of the history of our galaxy from this. Let me talk about transient events a little bit. This is near and dear to my heart. The Kepler spacecraft has found, it's no longer operational, but in its course, it found 5,000 to 6,000 planets around other stars. And what it did was, if this is a star, this is going to be a star a lot. And a planet is orbiting around the star, you can't really see it. The star is too bright. But if the planet is orbiting in the plane of your view, it's going like this. Every time it goes in front, it's going to block a little bit of the light from that star. And there'll be just a little bit of a dip in the light curve. And if it's regular and repeatable, then you can start assuming it's a planet. All right. I like to mention the Kepler because the last director of the science office was Dr. Jeff Coughlin, who's a Bremerton resident. So we got some famous people around. These are galaxies. Okay, now we can look even further past stars form galaxies. And when we look back in time, we're looking back in space. So the further back we look, the more distant galaxies, that light left a long time ago, at an earlier time in the universe. So by looking further back and then closer and closer and closer, we can watch the evolution of the universe happen. As we go back, for example, I talked about how stars bring in hydrogen and helium and regurgitate heavier materials. When we look back further and further, we see less and less of those heavier materials, less carbon, less oxygen, less gold, right? Because they just hadn't been made yet. So by looking at, like I said, tens of billions of galaxies, we can actually watch the universe evolve over time. Our own galaxy is hard to see. We're about 30,000 light years from the center. And it's a lot of dust. And if you looked at the Milky Way on a nice night in a nice place, you can see there's a lot of stars and a lot of dust in there. So it's hard to see through. So there's a lot about our galaxy we don't know. But by looking at these other galaxies, we can figure out a lot about what's going on in ours. Also, there are two conveniently located smaller galaxies in the southern constellation. I said we're about 15 to 30,000 light years. We're about 30,000 light years from the center. Well, 160,000 light years up in the southern hemisphere is the Large Magellanic Clouds, and 200,000 light years further, 200,000 light years out is the Small Magellanic Cloud. So we can actually individually watch stars in another galaxy and find out how these work. I love explosions. Explosions are the best, right? So these are supernova. Supernova produce a lot of elements. They're massive collisions. There's a lot of physics that we just can't repeat on this planet. That's a great thing about astronomy. That's our laboratory. You can't run a lot of this stuff on Earth, okay? These things detonate, and we've seen thousands by now. We've seen thousands of supernova detonate. This observatory, over the course of the 10 years, will see something like 10 million. All right, so we'll have a bunch of cases that we can study. But not only that, we're making a movie. I said over 10 years, we'll have 800 images each of these objects, okay? Well, when a supernova goes, we don't know what it looked like before. We don't know what happened because it wasn't visible to us. Now we just roll the tape back. Now we just go back and look at the previous images and we see what it looked like over time. We can actually watch the whole process happen. I had to show a couple more because these are so pretty. Okay. Tidal disruption events. I think you know how the tides work. Here's the Earth, and here's the moon pulls on the Earth, and it pulls harder on the near side than the far side because gravity is a function of distance, and it stretches things out. Well, that is taken to extreme in a lot of cases in the universe. If you have two stars orbiting each other very closely, the more like a large star a main sequence star orbiting a white dwarf, for example, the white dwarf will start tidally pulling in mass from the larger star. And as it pulls mass from the star, that mass will spiral in at tremendous speeds onto the white dwarf, for example, and it'll glow. And so we can see that. And if it's white dwarfs, let's see, white dwarfs are what will happen to our star after it's done burning up, using up its fuel. It's like taking something the size of the sun and shrinking it down 1,000,000 times to the size of the Earth. A teaspoon of a white dwarf on Earth would weigh about 5 tons. Okay, bigger stars are neutron stars, and now you've got so much mass that the electrons orbiting the nuclei are crushed together even further. And that's like taking something the size of the sun and shrinking it down to the size of Bainbridge Island without the traffic. So so these are more energetic events. These are, and it's got stronger gravity, right? So it's going to produce even more radiation. And then bigger than that are black holes, which actually poke a hole in space, as far as I know. It's a real cartoon. Those are real. That's the Crab Nebula. That's Cassiopeia A. That's supernova. Oh, this is supernova 1987A, which is actually in the Large Magellanic Cloud. Those are real. That's a cartoon. My next cartoon is of two neutron stars pushing together, merging. So when two neutron stars merge, that's called a kilonova event, and that produces gravitational waves strong enough that we can measure them with the facilities on Earth. That's a new field of astronomy. That's not light. That's actual gravitational waves. They also produce copious amounts of neutrinos, which are objects with such little mass, we haven't been able to measure the mass. We just know it has mass. They have no charge. There are about 1,000 neutrinos passing through my finger every second. And almost all but maybe 3 of them will hit something as they pass through the Earth. All right, very hard to measure. And they produce gamma rays. Black hole, neutron star merging with a black hole, even more energetic. 2 black holes merging, that's a cartoon. Even more energetic. So they produce these signals that we can't measure. But here's the deal. Okay, we have gravitational wave observatories. Right now we have 5 of them. Italy, Japan, Louisiana, I don't know what country that's in, and Hanford, Washington. This one's the Hanford, Washington. We have neutrino facilities. This is a small one, Super Kamiokande in Japan. We use even much larger facilities to measure neutrinos. And the gamma ray observatory has to be in space because that doesn't penetrate through the atmosphere. But the deal is when they measure these things, they don't have very good resolution. It's really hard to get good resolution with gravity waves. These fields are in their infancy. So when they measure something, they can say, it's right here, right here. And now you have to find it. Well, we'll have images of all that, right? Anything that happens in the southern hemisphere, we'll be able to find right away. And that's a key, because as soon as we find it, as soon as we pinpoint it, then you can apply other telescopes to look at it. Telescopes more designed for that field, right? So that's a big thing. Every time, and I haven't mentioned this yet, but every time, after a couple months, every time we take one of those 30-second images, it's immediately compared to an amalgam of previous images of that same area. And if anything changes, it sends out an alert in about a minute, and it sends it out to the public. And now follow-on telescopes can look at it immediately. That's a huge thing. Lenses. Gravity bends light, okay? And so first I'm going to talk about micro lenses. So I talked about how you can find planets around other stars. If they're orbiting and they orbit in front, they'll block the light. But if the planet's further away, if it's much further away from the star, okay, we won't be able to see it that way. But what'll happen is light leaves the star and it gets bent by the planet, the gravitational pull of the planet, the curvature produced by the planets being in the universe. And it focuses back and it acts like a lens. And so it gets bright. If you've ever been in a pool and it's a sunny day and the pool's got waves in it, you look down and you see all the light shimmering and everything. Some of it's being focused and some of it's not. That's what happens. We can find planets that way. There are stronger lenses, which astronomers call strong lenses. And they allow us to look even further back in time beyond what our telescopes can do in a lot of cases. If I've got a quasar, which is a black hole that's feeding in a young galaxy that's feeding, and it's putting out copious amounts of light. It comes towards us, and with telescopes, it might be too far for us to even see. But it comes towards us, it's coming out, and it runs into a cluster of galaxies like right here. This is Abel 2218, no relation. As it hits that large, massive cluster of galaxies, it gets refracted, it gets bent, because now it's following a different path. Okay, it's not a great lens. I mean, it's a random assortment of galaxies, and so it's not going to come to a nice focus. We're probably not at the focus. But what you can see is, if you can see that, you can see these little these little arcs right here and right up here, those are images of the exact same quasar. It's just different images of the same thing. And so we can find these strong lenses, and then we can follow them on with spectroscopy. The spectroscopy spreads the light out even more, and it can see what everything is made of. And so you can get more information than just looking at a direct image. But we can find them for the follow-on telescopes. Another thing is those lights, those arcs take different paths. And so they arrive at Earth at different times. And so if you looked at maybe this arc at 8 o'clock and it flared up and something happened, and you say, okay, I know that 3 weeks from now, that's going to happen over here. And so I can prepare and I can watch for it. And also that time delay allows us to measure the expansion of the universe. And I won't get into this because I like you. That's a strong lens. There's a weaker type of lensing that we call weak lensing. If I had a whole mess of galaxies, if I had 10,000 galaxies, and I looked at them and I want to get their shape, their average shape. Well, you know, some of them are like this, some are like this, and some of them are like that, and there's all kinds of difference. But if I took 20,000 of the galaxies and average it out, I'd get the ball, right? It'd all just average out to a circle. But it won't, because the light that left further back has been warped and skewed. And so what will happen is, if you look at a large enough swath of the sky, which we can do, you're going to see a slight skewness. And from that skewness, we can mathematically deduce the path that light's traveled. And so we can actually make a 3D map of the universe using this weak lensing scheme. Pretty cool and very complicated. It's been proven already with earlier surveys. Finally, I want to talk about large structures. I talked about how it took almost 400,000 years for the universe to expand enough to where it was cool enough to where electrons could orbit about nuclei and become neutral atoms, and then light could escape. Before that, and this is the light that first light we see is called the cosmic microwave background. Before that, it was dark. We can't see anything. But the thing is, before that, okay, these were all charged particles. The electrons couldn't hold on them, so the protons were positive charged, electrons were negatively charged. And so it was a plasma. And anything that jiggled would produce electromagnetic waves, like acoustic waves, like sound waves. And they would propagate, and they would result in higher density. They would result in higher and lower density areas, just like sound waves do. Well, when the atoms combined with, when the nuclei combined with electrons became neutral, all that stopped. And those higher and lower density areas were frozen in space. And now they just expanded out. Now they're large now. They were much smaller before. And so you can't just like look at a certain area and figure it out. You've got to look at a large area and statistically deduce where those acoustic waves are. And we've made some progress on it, but this is going to be huge. So we'll actually be able to find out about the universe before light could even escape it, which I think is cool. The last thing I'll talk about is the last couple of years, a group has found some very large scale structures. There's this big arc. You can probably guess what they called it. The big arc. Okay. And then just this year, they released another paper. They found this big ring. I don't know if that's Latin for big ring. It's about 1 billion light years across. And so what that is, that's structural information about the early universe that's writ large now on the screen. And we can follow that, we can study that, we can find these large scale structures, and we'll understand more about the universe we live in, what it is, where it's going. And I'm all done. But now I'd love to take questions if you have any. The first question is, who is Vera Rubin? Vera Rubin was an astronomer who passed away just a few years ago, and she figured out some very fundamental information about dark matter. And I didn't even mention that. Matter is, we tend to think that matter, everything in the universe is matter and energy. Well, we found out that that gravity is responding to something that looks like it's matter we can't see, and it seems to be 5 times more prevalent than the matter we have. It affects the rotation of galaxies, and so there's like a big chunk of the universe that we don't understand. And in the late 90s, we found out that not only is the universe expanding, but it's expanding faster than it was before. And so, so now we're talking about dark energy, which is anti-gravitational. And it appears right now, according to the best theories right now, and keep in mind, we call them dark because we don't know what the heck they are. Okay, it looks like the universe is 5% matter and light, all the stuff we know about 25% dark matter, and about 70% dark energy. So, I mean, we're just thrown for a loop on this, but Vera Rubin did amazing work as far as dark matter, and she was, I feel, she was famous, but I still feel she was pretty undervalued, and I'm very happy that this telescope, which will learn a lot about dark matter, is in her name. Funding, this is mostly funded by the National Science Foundation, but Bill Gates put in a bunch of money for the mirror. Charles Simoni, he actually put enough funding where the telescope itself is called the Charles Simoni Telescope. And so the funding is there, and of course we've got help from our partners, Chile. Obviously, Chile's putting a lot in. Canada, France, Britain, Italy, South Africa, Croatia. And a lot of these are in-kind help, but it's pretty fun to get on meetings like just this morning, get in on a Zoom, and there are people from all over the world. So the funding's there, but I've been doing this. I started working on this project in 2008, and I taught at a community college, and so I spent my summers doing it for free, and retired 2 years ago. So now I can do it all the time, which is great, man, because you're doing all this work all summer, you learn this stuff, you get it, you get everything going, you get some work done, and then you go to school, and at a community college, it's all teaching. And then you come back the next summer and you're trying to remember what you did, and you spend 3 weeks trying to figure that out, and then you make some progress. And now it's all summer vacation for me. So there is funding, but it can be hard. And the thing is, if you get an astronomy degree, you are able to do so many other things. You can see just from what I've been talking about, current astronomers are pretty great computer scientists, and they get pulled. I mean, we've lost a bunch of people to Amazon, for example. But the legacy survey of space and time is set for 10 years. And they're not going to walk home with their telescope after that. There'll be something else, but that's the current mission.
And there's one last thing from the chat about the pulsar stars.
Yeah.
Are there any patterns, and in what are they made of?
Oh, pulsars. I believe pulsars are neutron stars, and pulsar rotates very fast. And so it's got an incredible magnetic field. And so radiation will come out at the poles very fast. And a pulsar, if it's rotating so that it sweeps across us on a regular basis, and these things are rotating like, I mean, super fast, and sometimes, but they're very regular bursts. But it's like it's like it's been compared to a lighthouse. When that beam sweeps across us, we measure a blip of gamma radiation, So they're large stars that died and became neutron stars. So how do you protect against political upheaval on a project like this? Is that your question? Right. Well, and there were quite a few. There was quite a bit of unrest. Was it 2020? Inequality in the class system really boiled up, and so there were riots, and it was a little tricky doing work on the telescope at that time. I like to remember that it's non-political, and I like to remember that when I look up and I see the space station, there are Russians and Americans cohabitating there. And so some things, even though look how we are. Look at our stance with Russia right now, and so you got to do the best you can. No, it's a legitimate question. You just do the best you can with what you got, and then you try to make sure you keep channels open. That's that was a cartoon based on the shape that was measured. So I'm sorry. Yeah, excuse me. So what Alan asked was that an actual image when I showed that interstellar asteroid? It was a drawing of what they measured, and they measured something of that unusual shape. It's an unusual shape, right? It's a long skinny piece. But yeah, so that was based on the data, not just a sample cartoon. Yeah, when the object is out, object left town a while ago. I mean, they're just passing by, right? But if we can find them fast enough, that's the beauty of this telescope. We can find them fast enough, then we train other telescopes and they can watch it constantly. And if they can catch it early enough, we might send a mission out. Isn't that awesome? That's never happened. Oh no, I'm sorry. I know. Is all the data we collect public domain? There are a couple of caveats, but in general, this data goes out immediately. So and it's available to the public, and that's unusual, right? Usually, academicians are very selfish about their data, and they want to hide it because they want to get published and everything. This is going out to everybody. It's a free for all. What you're saying is, I mean, if everybody's got access to the data, which they do, then it's available for people to pursue commercial interests like the mining, and that's true. It's a public event. You paid for this telescope, so you deserve something. You too, you paid too.
This telescope spots a pattern. Spots a pattern of an asteroid on a direct trajectory for the Earth.
Mm-hmm.
And you talked about sending out a mission because you're going to spot this 50 or 100 years ahead of time. What is the plan? What's the mission?
So if you find out an asteroid's on a collision course with Earth, what do you do about it? Okay. The short answer is less karate, more judo. If you detonate the object and you explode it, now you've got a bunch of stuff coming back at you, right? It's all in the same trajectory. It's still coming at you, but now it's a bunch of it. Or if it's long enough, it's going to coalesce back together. So destroying it doesn't work. But if you can nudge its orbit out of the way, that's just fine. And you've got plenty of time. So you know what it's like. Just a little nudge over 50 years will do a lot. So there are a couple of examples. You can put a larger spacecraft near it and it will gravitationally adjust it so it moves out. You can put rockets into it and turn it into a rocket ship and slowly thrust it out, but being careful not to disturb it, right? You can even tag it. So the sun affects orbits. So if you put carbon black over one side of it, it'll affect that orbit and it'll move it away. So more judo, less karate. You may have read about this. There was an intentional collision of a spacecraft with an asteroid, and they studied what happened to it afterwards. And so they've been following that. So they're starting to run those experiments. Sarah Greenstreet at the UW was part of the DiRAC Institute, is constantly running algorithms and starting asteroids far away and seeing how close they get and looking at how it's affected by Earth's gravity. So yes, we're spending a lot of time working on that already. Oh yeah, intelligent life. Hey, we did it. I think what we'd look for is what intelligent life produces or may produce. So we probably look for visual or radio signals. Actually, Jim Davenport at the UW has worked a lot on this. How would we determine how would you send out a signal to show that you were intelligent life? And they've done a lot of work on that. We look at the atmosphere. Oxygen atmosphere is very rare, and the only way we know that it comes from is biological. There are other sets. Methane. We've been looking at methane on Mars, and I'm not talking about intelligent life. I have no idea what intelligent life is like. Okay, but I'm just thinking about life, and so like methane is a great indicator of a possibility of life. It has non-biological sources, inorganic sources too. But yeah, so we'll look at that, and what we'll do is that's going to be more spectroscopy from telescopes. So that'll be more follow-on from what we find. And the next one was more about metaverses. I think I was able to give you a 3-minute history of the entire universe because I skipped a lot of stuff that we don't know, and that's cool. I mean, a lot of people want to say they know everything, but we don't know. We go back in time and we get back to this small ball. And we don't really know what happened before that. And we don't know, we can do the physics and extrapolate down to small fractions of a second before what we call the Big Bang, which was a derisive term. But we really don't know what's going on. And there are theories like, okay, and these are well-published theories like, okay, we've got a matter universe with time moving this way. It would work out in physics if there was an antimatter universe at the same time moving backwards in time that was opposite. And there are a lot of theories about that. There's a lot of theories about dark energy, what it really is. You know, it may not be just some anti-gravitational force. Is dark matter particles that don't have electromagnetic force, or is it something about gravity that we don't know about? There are a lot of questions, and this telescope is going to give us a lot of answers about that.
First of all, thank you. This has been great. It's just fascinating subject. I have a very mundane question, and that is, what am I looking at in this picture? Is the telescope in that little round planetarium thing?
Oh, okay.
I see the barn sitting on top of.
So this dome, this is the main telescope. Okay, that's the dome for the main telescope. Down here is for resilvering the mirror and for the servers, for all the computers we use in offices. Down here, thanks for spotting this. This is the auxiliary telescope, or the oxtel. We're not very clever. And what it does is every night it will look at it determines the seeing. So sometimes you have more water in the atmosphere, or the seeing is not as good for other reasons. What it does, the auxiliary telescope will look at certain reference stars when they know how bright they should be, and they'll measure how bright they are, and they'll feed that information into the data for the primary telescope. So that auxiliary telescope is already being used to test other equipment. So thanks for asking about that. And you can see how tiny these cars are compared to the entire facility. Dane?
Yeah, just with the field of view that wide, what's being done about Starlink? Because isn't that going to be a pretty big factor?
That's been a big factor. And so the question is, what happens with the Starlink satellites? And that's getting worse and worse. You know, we've got thousands of satellites in orbit, and it's making near orbit, low orbit Earth's low orbit a dangerous place to be. So far, we're able to remove a lot of that information, but it's a hassle, and it detracts from the work. One of the things we're looking at is, I talked about 30-second images. We're waffling between one 30-second image, and we can still remove stuff from it, but we're waffling between that and taking two 15-second images. And that way you can compare the two, and it's easier to get rid of things. But that takes a little bit of time, because you gotta download the pixels and then reload. So we're still working on that. But yeah, that's also people. Somebody in our group has been working closely with Starlink and other groups to try to minimize their effect. And so, you know, like, can you paint the satellites black, for example, and be less reflective? And then that's a hard thing, because you want the satellite to be able to emit heat too, but they've been receptive to that, and so there's been something. But I know that some satellite groups are trying to put up massive satellites, and that's no bueno.
About how often the mirror or components have to be resilvered, and then the largest lens, that I assume that's a refractive lens, is that built with regular processes? What's it made of?
I don't know where that large is. Oh, so the question is, first off, how often does that mirror have to be silvered? And I don't know. I knew at one point, but there's a beautiful video. If you go to Rubin.org, it just got silvered about 2 weeks ago, I think, 3 weeks ago. The vacuum deposition, yeah, and it's a couple different layers with the silver, but I mean, it comes out, it's beautiful, but I don't know how often that happens. And the largest lens, how is that made? I don't know how that was made. I can tell you about the biggest mirror. And they're both pieces of glass, right? That big 27.5 foot diameter mirror. You take it to University of Arizona, you melt a whole mess of glass, you spin and cast it. So you spin it so centripetal force gives you the surface you want, and then it takes about a year to cool, because you don't want to crack it, right? But that thing took a year to cool just to get it prepared. Yeah, and it's got some actuators, so you can adjust the mirror just a little bit to compensate for atmosphere. Tom, you had a question.
If this covers the southern hemisphere,
Yes.
then is it likely that there'll be another telescope for the northern? Because you could get asteroids coming from there too.
Yeah, that's a great point. I know there are different projects looking at it. So there's smaller scale projects looking at it. We cut into the northern hemisphere a little bit from Chile so we can catch the ecliptic, so we can catch that area. But there are some, if this is the plane of the solar system, there are some that have a bigger tilt. But also that means that if they have that big tilt, that they're going to be coming into the southern hemisphere as well. So we should see most of them. Yeah. Right behind Alan.
How much of the funding is from the United States, and is it politically based like every 4 years?
How much funding is from the United States? There's private funding, but most of it is National Science Foundation. France and Canada and England chip in, and Chile. I mean, and a lot of different countries are providing in-kind help. The telescope assembly was built in Spain. There is a lot of computational work being done in Italy, and I'm a co-author on a paper that's coming out probably in about a month on I got a paper coming out, and I'm like the 4th co-author of 12, and I'm the only non-Croatian. So there's monetary, but there's also in-kind time that's been put in. Oh, he's a big boy. Yes, sir.
Do black holes explode?
Black holes are often, do black holes explode? That's a good question. And there's a lot about them that I don't know. So black holes, they come from explosions. When a big star runs out of fuel, it's going to collapse down, and it'll collapse down. If it's big enough, it'll collapse down so much that nothing can stop it from punching a hole in the universe, basically. And we don't really know what happens inside that black hole. So this is what I've wondered, and I don't know how scientific this is. If it sucks in, is it creating a large explosion in another universe? We don't know. There's the physics, all our physics breaks down. And then that's one of the reasons for this telescope. That's a good question. Yes, sir.
The Einstein's equations for relativity, you're using those like they do in GPS satellites and everything, I would think.
The GPS satellites have to use relativity, and they're not gonna get the right. Oh, so so is this going to another? What exactly is your question? I'm
elongations and all kinds of things that may be happening with that.
Actually, the weak lensing I talked about and the strong lensing is an effect of general relativity, and so that's happening. The GPS satellites, then I don't think they'd be really correlated to what we're working on. But you're right. I mean, for those GPS satellites to work, they have to use relativistic effects, so they're going to be off by quite a bit. I did some work on radiation belt electrons and protons spiraling around magnetic fields, and if you don't use relativistic equations for that, nothing happens. It's like we're rotating at this latitude, we're rotating about 700 miles an hour. And the speed of light is 186,000 miles a second. So those effects aren't gonna be as important.
Yeah, and the question was there, how much local things affect your light, basically.
Okay, yeah. So like the satellites, and I don't know if you've ever been to Hawaii on Mauna Kea, or actually on the Big Island. The lights are all designed so that they come down so they don't interfere with it. So that's one of the reasons we're on Cerro Pachon is the darkness, and the satellites that get in the way. We have to account for that. I don't think I perfectly answered your question, but we could talk later.
I'm gonna take about 3 more questions from
People by and large haven't asked questions before.
You're by and large.
Oh, pretty large. How about active tracking? Do you do that with math, or do you actually move the mirrors to actively track to isolate for the Earth's motion on a 30-second exposure? You know, if I'm doing it with my telescope, I get streaks. So I need a tracking mount.
It'll be minor tracking, and you can see, and so the major tracking is in between, but there's minor tracking during the exposure too. And that's tricky, right? I mean, it's a big object and you've got to move smoothly because you're working at this kind of resolution. The entire, when we slew, the entire telescope moves. And that's why it's got to be so squat. So yeah.
There's one more question from the chat box. And that's exactly what is your part in all this?
My part?
Yes, exactly. And what in your exact research?
So mostly I'm using the codes we've developed to I'm working with a fake universe. We've got this fake universe that we test everything on because we have a software pipeline that has to come on. It's got to be ready to work right away, and we've got to be able to analyze things. So the stuff I do is pretty boring. Like so I've been looking at white dwarfs, and I've been categorizing using machine learning technology by color in the 6 different filters, and using that to classify them. And by doing that, we're using something called photometric distance, which has not been done before. But by classifying them by color and knowing how bright they should be, when we measure objects of that type, we can say, okay, it's really this bright, but we know it should be this bright, and therefore it's this far away. And so I've been working a lot on distance measurements, and I just finished that. And lately I've been working on how to find variable stars like R Lyrae stars, which fluctuate on the order of a fifth of a day to a whole day, and categorizing them. We're using a lot of AI and a lot of machine learning technology, a lot of complex algorithms. This stuff, the calculations that I would run in the year 2000, that would take days, I can do in seconds now. And some of the calculations I run couldn't even been done in the year 2000. So we're developing new algorithms to take advantage of our ability to look at everything and run faster. That's a huge part. The people I work with, they're all PhDs in astronomy, but they could just as well be PhDs in computer science and statistics, because you can't look at all those pictures. Did I wear you out? Oh.
And I want, if there are a few more questions, Dr. Abel said he can stay just a few more minutes when we go up there. So if you have more questions, you can ask. And thanks so much. It was a wonderful lecture.
Thank you.